everyone, and welcome to 1337's Wednesday Knowledge Stream. I'm Madde, and I'm here to bring you some knowledge straight from the 1337 office here in Lund. Today is actually my last stream for the season, but we do have one more coming up next week, which will be hosted by my colleague Andreas Cederström. But since it's the last one I will be doing, at least, I thought that I wanted to think back a little about these past weeks that we've had. So we have had so many different interesting speakers and topics here with us. We've learned about mob programming, we've learned about Flutter and ethics in software development and multi-tenancy, just to mention a few. And we have been through some hiccups. I've had my head cropped. I've faced connectivity issues and sound issues. But anyway, it's been so much fun. And we have learned so much, every one of us, behind this, both about the sessions themselves and about the technical aspects of hosting a stream. So it has been so much fun. And I just want to thank everyone that has been involved in this. There is a lot of people involved, actually, that you don't see. So thank you for all of you. And thank you to all of you who have been watching this, because without you, it would have been nothing, right? So it's been a really good journey, and I look forward to the autumn to see more. But anyway, let's get started with today's topic. We will learn about solving three business problems with machine learning. And with us to teach us about that, we have no one other than the Wheels of Fury, Michał Łusiak. So, how Michał?
Hello, good morning.
Morning, yeah. Well, I know you have a little different rhythm than I do. How are you doing?
It's all good. It's a nice weather outside, so it's all good.
Great. You're really becoming a Swede now that you talk about the weather.
I know, but you appreciate the days of nice weather in Sweden. So.
Resistance is futile. So, how come you got interested in machine learning in the first place?
So I studied at Polish University, and Polish universities has this idea that to be a programmer, you have to study math and physics and electronics for first 3 years. So you get like, the math is put into your brain by force.
Yep.
And then at some point of working as a backend developer, because this is still what I do most of the time, I started like looking what's interesting out there outside of what I do normally. And suddenly I found like a place where you have like a lot of data, a lot of interesting calculation, and actually you have like a use for all those like algebra and calculus you learned in school. So that got me like interested in the first place.
Cool. So I say that we should get going. I want to hear more about it. I know basically nothing about machine learning, so I really look forward to it. And as usual, if you in the audience have any questions for Michał, you can, of course, post them in the chat, and I will ask them after the session. So I say the stage is yours, Michał.
All right, cool. So we're going to start with just a brief discussion what is machine learning, maybe touch a bit about AI and so on, and then we're going to get to the topics of the business problems we're going to solve. You've made the introduction of me, so I'm just gonna start with like the picture I always use in my presentation. It's taken from International Space Station, and it shows two places I consider home right now, because it's where I come from in northern Poland, and where I came to Sweden and joined 1337. So I love that picture. So let's talk first about like machine learning versus AI, because those things are like quite often mixed, those terms, and I'm gonna just give my take on this, how I look at those two things. So when you look into the media, that's how you usually have like AI presented. There's gonna be like some not understanding technology that's gonna came for us humans and destroy us. But in reality, it looks more like that, and there's like a lot of charts, formulas, and stuff, and also, it's a bit of a joke that like Matt Veloso put on Twitter, but it's a joke, but maybe it's not. It's funny because it's true. Like if it's written in Python, it's probably machine learning. If it's written in PowerPoint, it's probably AI. Because people who generally talk buzzwords, do like business presentation and so on. They prefer to use AI as a wording, but programmers probably like to be more specific and say they're using like machine learning, data science, or like even more specific algorithms. I see it a bit more like that AI is like very wide term that takes a lot of in, and machine learning is part of it. And if you want to be like more specific about like part of machine learning that's been like doing the most interesting stuff in recent years, which is like deep learning, which is machine learning using deep neural networks. So if you look at the Wikipedia definition of artificial intelligence, it's like kind of fluffy. It says that it's intelligence demonstrated by machines, and it shows like and mimics functions that humans have, like learning and problem solving. And I think also as a humanity, we have like kind of the moving term of like what AI is. It's kind of like a white rabbit that we're chasing. So like this picture of ENIAC, the computer from the 40s that was designed to do like calculate ballistic tables for the US Navy artillery. And by the time it was considered artificial intelligence, artificial brain. But now our phones can do those calculations, and it's like nothing impressive. So we don't really consider this artificial intelligence, it's just like using trigonometric functions for calculating stuff. In 90s, Garry Kasparov was beaten by the computer in the chess game, and by then it was considered also like an artificial brain. But by now we have pretty much like the chess of game mathematically solved in that way that you can calculate best moves for the next 8 or so moves, and it's pretty much solved problem computationally. It's still a very interesting game, and the way computer play chess is impacted how human plays chess, but it's generally like a solved problem. In recent years, we've seen a similar movement in like using deep neural networks to beat games like AlphaGo. Go with the AlphaGo algorithm from Google or Alphabet, and they also like took like a take on games like StarCraft, which they also put very interesting things. So right now, I think we still consider this like AI because we don't have like most people don't have a good grasp of like how neural networks work. But I think in a couple of years, it's gonna be like more and more demystified, and we're not gonna consider it anything magical, and we'll probably find another thing to call AI. And machine learning is more like the definition is like more solid, and it's like the scientific study of algorithms and statistical models, and basically it's about creating algorithms not by writing specific instructions, but using patterns and inference to like create those algorithms. So there are a few types of algorithms, a few types of groups of algorithms used in machine learning. One of them is supervised learning, and supervised learning is the kind of learning that we need to provide data with patterns for the algorithm to learn. So when we do normally programming, like as developers, we take some input data, we design algorithms that will generate the output and solve the problem. With machine learning, it's a bit different because we take inputs and outputs that are sample data. We use training process to generate algorithm out of it. And then we're using this algorithm to the process called inferring. So we get new input data that the algorithm haven't seen. It's different than the input data we use for training. And based on that, we can create predictions. So basically using that algorithm that we generated from input and output. And the algorithm is like looking for patterns in the data, and yeah. So one of the like most common tasks used in reinforced learning, supervised learning, is regression, and this is basically predicting numeric value based on like features. And a classic example of that is like predicting the price of an apartment. So you take information about apartment, for example, like square meters or square feet, number of bedrooms, how close is to the train, and so on. We're just going to take for this visualization only one feature, because then with one feature we have 2 dimensions to visualize, with 2 features we have the 3 dimensions, and then it gets more complicated to visualize. Like mathematics will take a lot of dimensions, but for us humans it's really hard to visualize in multiple dimensions. So it just keeps easy, and make a prediction model for the price of apartment based only on like square meters, which is like quite common, very good prediction of the price. The bigger apartment, the more it costs. So we have to find some function that will match this data, and this is basically like how regression works: finding a function that will match our data and be able to predict new values for the data we didn't have in our input data. Another type of algorithm for supervised learning is classification. So we can classify apartments maybe as expensive one or cheap ones. So we take like a group of data and divide it into 2 based on some features. The basic way of doing this is like binary classification. So we have basically 2 classes, 2 types of outputs, but we can have also like multi-class classification. So for example, a good example is like taking handwritten data and classifying it to, like, for example, 10 digits. So we have like handwritten digits, and you classify, is this like 1 or is it 7 or is it 4? Another group of algorithms is unsupervised learning, which is probably much more interesting, because for supervised learning you need to provide a lot of data that you have to manually label. So there's like, it's a lot of work involved to generate the data to use for training that algorithm. And unsupervised learning, we kind of don't use that labeled data. We just use the data itself without manually labeling it to find something interesting in there. So this is probably where the more future lies, because those can be more automated with less humans involvement. But right now it's a bit like underdeveloped compared to supervised learning. We have much more things that work in the area of supervised learning. But one of example of like unsupervised learning is clusterization. So finding like a groups of similar apartments maybe within the group. So we can divide them into 3 different groups just by using its features and not looking at the generated output value. Okay, so let's go back to regression, which is like predicting a single numeric value out of our features. And the linear regression is probably like one of the simplest machine learning algorithms, and it's quite often used for explaining how the stuff works, and I'm gonna do the same right now. So we have some parameters and some values. Previously I used like as an example, the parameters was like apartment size, and values were like how expensive it is. And those parameters we called features, and values we call usually labels. So machine learning. And basically, like, let's start with explaining how the data looks on the 2-dimensional chart. So on the horizontal axis we have parameters, on the vertical we have values. So for value on the parameter side, for every parameter we should have some kind of value. And if we have value for every parameter and it's like kind of continuous, we talk about linear function. And there are like two variables to describe linear function. Those are a and b, and a is responsible for the angle at which we are, and b is responsible for kind of like a transition in the vertical line. So if the a equals 1, we have like line at 45 degrees. If the a is bigger than 1, we have like more than 45 degrees. And if the b is bigger than 0, then you kind of have a higher start point. So I kind of I like to use example that's like, you know, let's say in a perfect life situation, the older you get, the more money you have in your account because you're doing some savings and so on. And like with a equals 1, you're doing okay. You have like good linear increase. With a bigger than 1, you have like higher increase. So like you are able to put more money and so on. And like maybe the last example would be bigger than 0. You start with like some I don't know, trust funds by your parents, so you get like in much better start than other people. And also in data science, we like A and B are like used in like classical mathematics. And in data science, we kind of use values W and B instead, because they kind of fit names well. Because W is the weight and B is bias. So weight, we usually, in this case, we'll have like one parameter, we'll have more, and for each of them we'll have weights. And bias is basically all the other information that's not contained in our parameters. So let's look at example of predicting how much we'll pay for the taxi. This is like another good example of regression, because we use some features as an input, for example, distance, so how much you travel with the taxi, and based on that, we'll try to predict how much you're gonna pay for taxi, which kind of makes sense because usually there's like a price per kilometer involved in the price of the taxi ride. So to like fit the linear regression model, we start with like a straight line, just put like somewhere, it doesn't really matter. Then we calculate how much off we're from the proper kind of model. And for that, we use like error function. So this is like one of the error function that's quite commonly used. It's a mean square error, and looks kind of scary with this like sigma and so on. But when we like broke down into like more programmer terms, it's basically like a for loop over those green dots, and we compare where's the real green dot versus where's our line meets it, and where's like our prediction for that value. So we take a difference out of those, we square it up, and there are like two reasons at least for square it up. First, we remove the sign, so if it's like below a line or over the line, it doesn't matter. And also what squaring does is penalize the values that are the more far away from the perfect line. All right, so we we check how badly we are, and we try to find a way to get closer. And for that, we use like gradient descent, for example. It's one of the optimizing algorithms. So if you look at this chart, it's basically for values A and B, or for W and B. There are some values where the chart is has really high values, so error function is pretty high, and that's where we don't want to be. We want to find like the lowest value possible. So it's basically, imagine like you drop a ball into the bowl, and you want to find the bottom value of that ball. So basically the lowest value of the cost function for parameters A and B. And this involves like calculating derivatives and so on, and we're not going to really dig into this right now, because with the ML.NET you don't have to think about it. It's interesting to dig how those things work, but realistically you don't really need that with modern algorithms. So yeah, we find some function that's kind of fitting the data pretty okay. It's never going to be perfect with the linear function, because data is never perfectly linear, but it's good enough. It's the best possible function with that model. And now we can like predict the new value. Let's say we route the taxi with like 20 kilometers, and based on that, we predict that we're gonna pay 450, let's say, Swedish kroner. So yeah, we have a way now to predict a new data that our algorithm didn't see during training. So now let's jump, like when we have like some basic understanding how like machine learning work, let's jump to ML.NET. And ML.NET is like Microsoft's new venture into the machine learning. They use like high-level API, so it's more designed from the perspective of what goal you want to achieve, and not like what techniques you're gonna use. So for example, you want to solve regression problems. So basically, like, predict a number. So you don't really think about like, oh, I'm gonna use this online gradient descent with this and this. You basically start with like what problem you have to solve. So to use it effectively, you just kind of need to learn what kind of problems can be solvable with machine learning. So understand what's regression, what's classification, and so on. And it's basically like code first approach. So basically you do it by writing code, and they claim that's technology they use internally for years in products like Bing and Excel. It's free, it's open source, it's cross platforms, it's written in .NET Core, so it works very well within the modern .NET environment. They announced it first in May 2018, and they did very quick development cycles with every month releasing new version. And in 2019, the release version 1.0, so kind of production version. I think currently they at 1.4 stable version and 1.5 in preview, but maybe they announced something at Build last week that I missed. Unfortunately, they don't support like a usage of neural networks natively. But you can import models from TensorFlow, for example. It's still a bit finicky, but works more and more with every release. So the model of working with ML.NET is it's kind of all the usual model of working with data science projects. You collect and load your data into the you collect your data. So this is basically what we always start with data. And then you load the data into memory or other solutions. And they have a bunch of like kind of data loaders. So you can load data from text file, from CSV files, from SQL database, from like Azure storage. And then we build our calculation pipeline. And within this pipeline, we can do a lot of things like transform our data, because sometimes we're going to need to work with the data, like remove some values that are unnecessary, figure out what to do like with empty values. Like sometimes we have nulls for some columns and so on. We want to try to figure out something with it. Then we use like a feed function to train the model. So basically like the minimize the cost function. And then we can evaluate model, get some metrics, how well it looks, and work iteratively on the process. Or when we're happy with the trained model, we can save the model to the disk, to database, and so on, and use it in another project where we're gonna load that model and use to make predictions. So I'm gonna show mostly today how we do training, but then you can use that model somewhere else. So for example, you can have like a build process that will run the training every week, that will save the model somewhere in the cloud, and then your application will be able to like reload that model without like recompilation every week, and you'll have a new model working on the new data that arrived in the last week. So looking at the code, how we work on it, basically there's like a bunch of steps we always do. We always start with ML context. This is kind of like a object we'll be passing around. It's very similar context to like database context in the let's say entity framework. And then we use our data loader to load data. In this example, we do it load from text file. And there are like ways of parsing it. You can either manually pass the model on, like have an object that will be parsed similar to like JSON files are parsed and so on. Then we do the estimator, so basically our pipeline for things. So so we transform the text when we need it. We append our training algorithm. So in this case, it's binary classification. Then we do the process of fitting, so the actual training. And after that, we have like prediction engine that we can use to create predictions and put some sample input and predict what we did. So let's look at like more practical examples. So the predicting taxi fare is the one I talked a bit already, so we can start with that. And all the samples I'm gonna show here, they come from the .NET machine learning samples repository. it's a very cool place to figure out how to do things. They have a big library of different kind of problems that can be solved in this way. Example applications are just samples of code how to do it. So it's really cool place to start your adventures with ML.NET. So for the taxi ride, that's kind of the input data we have. We have some information like a number of passengers, how long the trip takes in seconds, how long was the distance in miles, was it paid with cards or cash, and per amount is how much you paid. So this is kind of what we're going to use as a output data, and everything else we can treat as an input data. Maybe not all of that data is usable. For example, number of passengers doesn't really impact price. Let's say that's a logic, but we're going to feed it to algorithm anyway. So first thing is we're loading the data from the text file. As you can see, I load two files, the training data and the testing data. That's one of the things we also do in machine learning, that when you have a bunch of data, you kind of divide it into 2 or even 3 sets, because you want to test your algorithm on some data that the algorithm didn't see during training. So usually you divide it like 70 to 30%. So you use 70% of the data for training and the 30% for testing. The analogy I'd like to use, so for example, if you have like a test and you have a sample questions for tests, you don't want to like your students to see all the questions, because they can memorize them and then they will just answer that, and they want to be able to generalize well the knowledge. So it's more like you want to see some sample questions, see what's going to be the questions on the test, but you want to generate like more generalized version of that algorithm that will also work on the question it didn't see or the data it didn't see. So that's why we divide the data into things. In this scenario, they have like 2 separate files with the data already divided. Sometimes you have to do it manually, so it takes like take like a bunch of data to one set and pick the rest to the others, but it will do. And then we do a lot of like data transformation. So so basically, there are some columns we call to the label. That's going to be our kind of like what we want to predict. We take other columns to like kind of column name features, and we do a lot of transformations of that column. So for example, we do like one hot encoding on categorical data. So for example, vendor ID. We do it because it's a numeric value, and so vendors will have like ID 1 to 7, 55, and so on. And we don't want the algorithm to look at the higher vendor ID. It means something, because it doesn't make sense. It's just like a number we given to the ID we given to the entity, and it's not really numerical in that sense that the higher the value, then it has some meaning. So we instead of change it into categorical data, so algorithms know it's not really numerical value. It's more like just that's different entities. Yeah, so we transform our data, and then we get into the actual training. So we pick like regression type of problem. We use SDCA regression algorithm, and then we fit the model. So basically use the actual training. And at the end, we just write evaluation. So when you look at the output of evaluation, you get some metrics. Loss function is the thing we talked about, the R cost function we're minimizing. And the number itself doesn't say anything right now here. It's more like we want to find the lowest possible for the data we have. So it's just like value get minimized. R2 score is like more informative, because for regression, it says how good the algorithm fits the data. It takes the value between 0 and 1, and 1 means it's a perfect match for the data, and 0 means it's like doesn't match data at all. So 0.7 is like kind of decent. Also, like with the ML.NET, we can do our usual .NET approach of what I like to call .NET-driven development. We take an object, we press dot, and we see what we can do with it without reading documentation. It's probably not the most responsible way of doing programming, but throw the stone at me if you've never done this. And by opening ML context, you can just see like different kind of things you can do with the data. So clustering, binary classification, regression, forecasting, and so on. So it's really easy to start using directly. And when you go to like the specific regression trainers, you see what kind of algorithms you have possible, like online gradient descent, SDCA, Poisson regression, and so on. Okay, so let's look finally at our first business example, and I'm going to start with a product recommendation. So this is the kind of thing you see, let's say, at Amazon or other places where you buy stuff, and you see like customers that bought this also bought those few other things that you don't really need in your life. So the input data we're going to use is already transformed in that way that we take a set of let's say invoices that have like multiple items on it, and we just put them in parse. So we kind of generate graphs of things that appeared together on the invoice. And for solving that problem, we're gonna use an algorithm called matrix factorization. But yeah, we're gonna start with like loading data from the text file again. We do some like column work and so on to get the data formatted in the way we like. And we pass some options to the matrix factorizations. There are some good defaults that you can use, but you can always like change them. So we mark which is our like index column and the row column. So basically like two different columns containing graph information. We define what kind of loss function we're using. So again, the cost function or loss function is the way we optimize the algorithm. Alpha is the basically how quickly we're learning that. I didn't talk about like learning speed, but this is like one of the hyperparameters that it's very often passed into learning algorithm and decide how quickly we do steps to find the bottom of the bowl. You don't want to do like too big of the steps because you can miss the most optimal values for the function. But if you do the value too small, it's gonna take ages to train. So it's a bit of like optimizing, and with the time working with algorithms, you get good intuition what works and what doesn't work. And yeah, we use the matrix factorization algorithm with the options we just generated, and we feed the model, and then we have prediction engine that will predict value for a pair of products. So basically, for products number 3 and 16, the predicted score is 0.4. Again, isolated, it doesn't say anything. Now we'll have to run this prediction engine for like every part of product, or like at least some limited set of products. And basically, the higher the score, the more common they were bought together. So you probably will like to sort that, pick the 10 with the most values to show for each product. So it also needs some like more steps and maybe some process to do it. At one other customer, when we implemented it, they had like this kind of build process that was calculating this all stuff every week on the weekend, because the data was changing seasonally and so on. And then basically like drop the output into the database, and then they could directly read that, with like time like that from database when the customer went to the product. Okay, customer segmentation. So basically finding a group of customers that are somehow similar based on, in this case, orders they have, and who ordered what. This is like some wine ordering thing, and we have like pivot table to put those together. So based on the data, we will try to find like groups of customers that do similar things, order similar things, and so on. So we can maybe create offers for them. Again, we're gonna, by the time now you figure out the drill, you load our data. It's a bit more complicated with the pivot tables here, so I wouldn't feed that code into the screen. It doesn't really matter. You can check the samples for the details later on. And this time we pick like a clustering algorithm, and clustering is a type of problem we're gonna solve, and we're gonna use k-means algorithm specifically here. And we train it and get some output out of it. And then we can evaluate the model, save the model to disk or to memory or to database, and reuse it somewhere else. Cool. Another problem that's very easy to solve is demand prediction. There are at least two ways to solve it. You can do it with regression that we talked before. You can use time series to kind of observe the regular things in the day. And the input data here we have, this is like a bike rental data. And we have like information about the date, and we also split that information about like which hour of the day it is, what kind of season it is. So this like winter or spring and so on. Is it a holiday? Is it what kind of weekday is it? So 6 is like Saturday, 0 is Sunday, and so on. Is it working day or is it like not working day? Also weather information. So temperature, humidity, wind speed. And based on that, of this historical data of the bike rental, we try to predict how many bikes will be rented today, so we can get them to charging station and so on. But it's also very similar with like what people buy. So for example, buying fishing gear is very dependent on like what's the weather outside and so on. And we've seen a lot of interesting examples at clients that show like I really like on beginning of the December is like some day in Sweden that you should supposed to change the battery in your fire alarm, and battery sales on that day will peak really hard in some retail stores. So it was really interesting to see that information. So yeah, again, we load the data from the text file. This time, even though it's CSV file, we can still use text file. And this time, I'm not really specifically say columns. We just used an object that can be like parsed. So you can have like much nicer architecture without like not dropping just like a definition of data in loader, but you can just have define nice objects and entities that you're gonna reuse across the board. We build our process pipeline again, where we just work on that data to be able to easier parse it. And then in this case, we're doing something interesting because we don't use a one regression model, but we use multiple of them. We drop them into some table. So then we can iterate over that table of regression models to maybe try multiple algorithms on our data to see what's gonna go best. So basically we're gonna train our data on multiple algorithms and find the metrics which did the best, because sometimes you can have an intuition which algorithm will best work on your data, but you can do basically experiment and manually try every algorithm to train. It's gonna take a bit more time, but sometimes it's worth it to spend more time training and experimenting to get a better results. And this actually gives a question: couldn't be done manual, like completely automatically? So recently, ML.NET introduced a concept called AutoML. So basically, they do that thing automatically for you. So instead of like creating like a list of algorithms, regression algorithms, and iterating over them to create them, you can create experiment kind of object with regression metrics, and run your data on the all algorithms possible. So this will cause the algorithm. You just define how much you want to take text experiment. So if we use the taxi data for 60 seconds, it managed to text 29 different algorithms, although not really, because you can see some of them are repeating. it's just not only try different algorithms, but also different input parameters to those algorithms to try figure out what's gonna work best. And at the bottom we have like the top ranked, so like light GBM regression turn out the best for the taxi data. So now we can use that model to make our prediction because it's the best algorithm for that thing. And yeah, then you can basically like use the best model and run it and have like the loss function R2 square and so on. So previously when you saw the R2 score was 0.7, with this model it's 0.74, so even better. And we have like even example prediction on the bottom. So that we predicted the fare will be $15.57, and the actuals were like 15.5, so quite close. Okay, so this brings the question: can we automate even more? Like, we don't want to write code, so of course we can. They created even wizards, so you get to the project, right-click, add machine learning, pick your scenario, load your data, decide how long it's gonna train, like 10 seconds. We start training, so basically like trying basically the same things we did before, like trying different algorithms on your scenario and your data to see which is gonna be the best. Then we look at evaluation and add code to the projects. Boom, you're a data science engineer now. But the question is, should you, if it's like moral and responsible? And I think it all depends on the case. Probably if you don't understand how those algorithms work, you shouldn't really use it on like medical data to decide, how you should treat your patients. But if you're experimenting with your, company's data, for example, on sales of stuff, and want to like predict some peaks or find some like relationships which you're gonna then, probably confirm with your salespeople and so on, then I think there's like nothing wrong with that. So I definitely think there's like a value of learning and digging into more algorithms and have better understanding how they work, because you're gonna get more productive and you get better results. And if you know how the algorithms works, it's really easy to use them from within ML.NET. But in some cases maybe it's not responsible, and you shouldn't do things like that, use algorithms randomly that you don't understand. So like there's a big power with it, and like the classic Spider-Man quote says, like, with the big power comes the great responsibility. So you should make the decision on your own what's good and what's not. I think it's really nice, low trouble way to get into ML.NET and start using it within your code, but you have to be cautious where you use it and how you use it, as always with every kind of piece of code you're writing. So that's all for me right now, and I guess we can take the questions and see where we go right now.
Okay, thank you so much, Michał. And just to let you know, I too am guilty of dot-driven development from time to time, so you're not alone. We did have one question here. So just for a general feeling, what amount of sales data would be needed to get reliable prediction on products?
Yeah, that's really like a question that's like hard to answer, because if you have like clear patterns, you don't really need a lot of data. But the more specific things you want to find, you need more data. I work with a client that had like over 1 billion rows of data of like 20 years, and that was too much. That was like too much to calculate. That was like really all the data of products that were already not in their offering and so on. So that can be a problem when there's like too much. But you can already get like, for example, decent amounts of, for example, predicting where sales peak with like around 1,000+ rows of data that they're like equally spread around the the year, to kind of find like seasonal trends. So I think like thousands is a good start. The more the better, but not always.
I am a bit skeptical of those predictions. I've noticed that I do get predictions, for example, when I buy clothes, and I don't like them at all until I realize that I've seen them so many times that I eventually buy them anyway. So it's kind of like I have a weak psyche or something, but it's not the machine learning, or is it? Do they know more about me than I do?
Yeah, that's an interesting question, because like there's also like this kind of, we tend to like things we see more and we know, so they can also be kind of like the opposite stuff. So basically by feeding you the stuff kind of impact your buying decisions.
Yeah, it's all intertwined.
Also, a lot of those predictions depend also on the quality of the data. So not only like the algorithms used, but the kind of the data used, how it's been prepared, how it's been cleaned, and so on. A lot of work in the whole process is actually like, you know, filling the gaps in the data and figuring how to interpret it. So even before we get to that, like loading data to the like text loader, ML.NET, or wherever you're gonna do it, you have to figure out, for example, how to treat nulls on your data, how to like treat the rows that you have like empty or some gaps and so on. So there's like a lot of manual work before we even get to that step. And some people more experienced in data science work than me say that sometimes it takes like, you know, 60-70% of the time they work on the project is just to clean up the data before they get to the actual
That's quite a lot.
Prediction.
But yeah, I guess it takes a lot of data to get good predictions. Another question here: since we have AutoML, is there any value in doing the process manually?
I'd say like, you know, the on the specific data that you actually like you loading, AutoML can show that, you know, that it's a better model for something. But in your specific situation, you want to use the specific algorithms because, like, for example, you know, it generally works better on that type of data. Or, for example, you want to have some explainability because there are some algorithms that are very, very black boxy that basically you cannot explain why they make decision. But there are other algorithms like decision trees where you kind of have like a track of why this decision was made better. So for example, in some areas of business where you actually need to explain what you make this decision, there's a lot of discussion, for example, in European Union to, you know, to only use machine learning if you can actually explain why you made that decision. So people can actually get information why they were like denied a, you know, loan or something like that. So there are algorithms that are better at this, that you can, you know, have better explainability compared to like neural networks that the explainability is really finicky and hard. And that's why, for example, Google says sometimes like a Gmail that this email is important for the reasons that Google understand, but they're too hard to explain. It's really funny, but like when you work with machine learning, you actually understand what they mean by that.
Yeah.
You know, run some neural networks and they cannot explain this output, but you know, it's actually pretty good probably.
Another question here: where to train the machine learning models, cloud versus on-premise? What is your personal preference?
So you can do it both on like locally, and you can do it on Azure and you know, on some other build servers, for example. It all depends into, you know, the amount of data you have and so on, because sometimes you have amount of data that will not fit in the memory of your machine. Then, you know, if you're like gonna do the production kind of training on the big sets of data, you probably want to do it on the cloud or on some dedicated machine. But if you're like just experimenting on smaller amounts of data, you get like much shorter feedback loop on working locally on your machine. So again, it depends what you're using for that. But generally on big sets of data, I would do it on the cloud because it's just like, you know, you have more power. You have like dedicated cloud machines that have like high power GPUs optimized for doing this kind of stuff. With like especially neural networks, you want to have a good GPUs because it's a lot of like matrix multiplication that GPUs are really good at.
It's more convenient, basically.
Yeah, in many cases, yeah.
Going back to what you said about tracking the decisions it made, the algorithm, I thought about, I don't know if you've seen the machine learning generated Eurovision Song Contest song. Have you heard about it?
No, I didn't.
They just took a lot of Eurovision Song Contest songs and fed it into a model, and then they generated a new song. It was so hilarious, but it would be interesting to hear how did they decide about those lyrics. It's hilarious. I recommend to check it out because it's super fun.
Yeah, there's like there's a lot of there's like the whole area of like sequence generation using machine learning. It used like recurrent neural network. I did a talk about like generating like heavy metal riffs using that kind of things. And you know, there's like a lot of interesting way to do it. So for example, in the StarCraft example, when they played StarCraft using thing, they use that kind of source to like generate the sequence of like keyboard strokes you do to like play a game. So you know, you think it's gonna be only good for like generating like, you know, fake poems because, or you know, fake lyrics and so on. But there's like a lot of ways where, you know, stuff is in sequences and you can use that kind of things to generate sequences. So it's very interesting that a lot of people try algorithms that were designed for one thing to do completely different things, and actually surprisingly they work in funny way.
Yeah, I guess it's just about coming up with a crazy idea. So that was all the questions that we had. So thank you once again, Michał, for doing this session. It was interesting to hear. And once again, thanks to all of you who have been watching both this and the other sessions. As I said in the beginning, next week, Andreas Edström will be hosting the next stream, which will be about Dapper with Per Öqvist. So don't miss that. It will be really fascinating, I think. So bye and take care and have a great day.
Bye-bye.